Oh, hello, everyone. Welcome to today's row. We have actually two talks today consecutively. And it's a pleasure for me to introduce the first speaker, Justin Starreveld. I'm sorry for the pronunciation. I'm pretty sure that it was not right. So Justin is now an AI and data science consultant at ION, which is a consultancy company in the Netherlands, is working at the moment on data analytics, AI to make better decision. But he recently graduated from University of Amsterdam, who was working with Professor Dick den Hertog and Sophie Luxo with the intersection of energy and decision making. And today he's going to talk about his work during his PhD, and we are all looking forward to hear. Justin.
Yeah, great. Thank you for the nice introduction, and thank you for the invitation to be a speaker here today. Yeah, so I'll be talking a little bit about some of my PhD research, specifically two of the chapters that appear in my thesis. And as it is already mentioned, this is a collaboration between the University of Amsterdam with my first supervisor, Dick den Hertog, and the TU Delft with Sophia Luxo. And the title of my PhD thesis was the following: Mathematical Optimization Under Uncertainty with Applications to Hydrogen Deployment in the Netherlands. It's a very long title, but I'm going to introduce it step by step. I want to start with a quote from our soon-to-be Prime Minister in the Netherlands, who says, hydrogen will play a major role in our future energy system. I think he's not yet officially Prime Minister, he'll be in a few days, but a very promising quote. Sounds interesting, but what is hydrogen? Well, if you remember from your high school chemistry classes, hydrogen is one of the atoms in the periodic table of the elements. And if you put two of these hydrogen atoms together, you get a molecule that is quite energy dense. So it's an interesting molecule to be used in the energy system. And one of the promises of hydrogen is that you can create it in an environmentally friendly way using renewable electricity and an electrolyzer. And then because hydrogen is quite an energy dense source, you can use it for industries such as aviation and shipping and chemical manufacturing, which are industries that are otherwise quite hard to decarbonize using only electricity. So this is the idea at a high level. This is why hydrogen is an interesting energy carrier to be used in the future. And there are lots of plans surrounding hydrogen in the Netherlands. We have a very strategic location. We have a big shipping industry, we have a big aviation industry. We have some natural advantages with the North Sea being a nice place for offshore wind development. We have these underground caverns that can be used for storage. We have a large natural gas infrastructure already that can be repurposed for hydrogen. So lots of things, advantages for the Netherlands to convert their energy system into more hydrogen-based system. However, there are issues, namely that there's lots of uncertainty surrounding this. You can think of the economics. Is this going to be economically viable? All these investments. How about the technology? How are things going to change over time? Politics, etc. Lots of things that are quite uncertain, which is why hydrogen is struggling to get off the ground a little bit. But it's a nice setting to apply some robust optimization. So that's what we're going to be doing today. And that's what we did in my PhD research. So one of the case studies we focused on was the following: a small industry cluster in the southwest of the Netherlands, bordering Belgium. And in this cluster, they have a large oil refinery, a large chemical producer, and a large fertilizer producer. And these companies all have to reduce their CO2 emissions over time. They have the goal to be net zero by 2050. But they're not quite sure what their strategy should be for decarbonizing. Should they switch to hydrogen? Should they convert certain processes to be electrified? Should they use carbon capture and storage? It's not quite sure which strategy is the best here and what mix of things to do. Uh, and also, there are some questions about the infrastructure in the region. Do we need to expand this infrastructure? Do we need to build new pipelines, etc.? Yeah, so these are some questions that we would like to answer using mathematical optimization. So they created a model, and in the model, the objective is to maximize the total profit for this industry cluster. We have a very long time horizon from 2020 to 2050. We have about 160,000 variables, of which 5,000 are integer, and a similar number of constraints. And one of the most important constraints that I already mentioned was that they have to reduce their CO2 emissions. And this is a linear reduction over time, where they have to reach the target of 55% in 2030 and net zero by 2050. Okay, so we can construct this model, we can solve the model, and we can get an optimal solution, as we see here on the screen. This is a very high-level overview of the solution, but it tells you roughly, okay, this is how much you should invest in which year and in which decarbonization strategy. So that's great. The model also spits out that we can run a profit over these years, so these companies can keep running while meeting their CO2 reduction targets, is the idea. However, if we go back to our model, we also have 600,000 parameters, and many of these parameters are highly uncertain. So optimizing only for a single scenario is not really very robust. To give you an example, here we have the natural gas price for the Netherlands, a yearly average. And at the start of my PhD in 2020, in collaboration with other people, we made a forecast for the future up until 2050. And for 2020, the forecast was quite close. But for 2021, suddenly COVID came and shot the price up. And then in 2022, there was a war in Ukraine, which caused it to deviate even further. So here we see sometimes there's a big difference between the forecast and the actual reality on the ground. We can, of course, adjust the forecast, which is what we do for the next years. But I wouldn't trust that the dotted line will be what reality will actually have in store for us. So this is a bit of a problem. We can optimize for the forecast, but what if the historic data, if the real data is different, then we're optimizing for something different from reality. So essentially we have a mixed integer optimization problem. And in our case, we discussed with all the experts, and they said most of the uncertain parameters for this problem are in the objective function. You could say that some are in the feasible region, but these were not considered that important. They really wanted to focus on this objective function. And some examples of these parameters are the prices for various sources of energy, the emission tax, a tariff on CO2 storage, and some other financial parameters. These were considered the most uncertain, and we focused on taking these into account. Okay, so the question is, how should we deal with this uncertainty? If we don't really know what we're optimizing for, what is the best approach here? Well, you can look at the existing literature, and in 2018, there was a study done by you et al. Who looked at uncertainty assessment methods in energy system optimization models. And this is a very interesting study because they came up with a few conclusions. The first one was the importance of uncertainty is commonly acknowledged, but a minority of papers actually use a formal methodology to deal with the uncertainty, which is a bit concerning. Huh? Their second finding was that the most popular method used in the literature is actually sensitivity analysis. And the least popular method was robust optimization in these energy system optimization models. So a little bit concerning. I'm assuming most people in this webinar are proponents of robust optimization. So why is this not being used in the existing literature as much as it should be? Okay. First, I want to focus on this this statement, the most popular method is sensitivity analysis, and then later on the third statement. Because we're not really happy with this conclusion that people are using mostly sensitivity analysis, because we don't think it's really enough. It's not showing us the risk involved with decision making. Essentially, uncertainty in sensitivity analysis, you first get to see the uncertain parameters, and then you get to re-optimize your decisions, and then you check what are the outcomes. But this is not very realistic, because in reality, you have to make certain decisions now, and only later do you get to see what the uncertain parameters will be. In robustness analysis, which is a bit of a counterpart to sensitivity analysis, we have a different objective. We're now analyzing how changes in the parameters of our problem affect the performance of a given solution. So here it's the other way around. We first have to make the decision, X, and then we get to see the realization, Z. And the idea is that this is a more realistic depiction. You have to make decisions now, and only later do you get to see the uncertain parameter Z. So we would argue that robustness analysis is more interesting in practice if you want to really stress test a decision. Are we making good decisions? And sensitivity analysis really is more an analysis of the model and how the optimal solution will change. The algorithm for robustness analysis is very simple. We just define a set of scenarios that we would like to analyze and a solution, X bar, and then we can analyze the performance of X bar with respect to each scenario in our set of scenarios. 2 lines of code in this algorithm, very simple. But you can, of course, argue that this is actually not very realistic, because if I'm fixing all my decisions now, regardless of what the scenario would be, then I'm fixing a lot of decisions. In our case study, we're making decisions up until 2050. To say that all these decisions must be fixed now in 2025 is a bit too conservative, maybe. In reality, decisions are often made sequentially. So that's what we try to do. We want to extend robustness analysis to a multi-stage setting where decisions can be made over time in a more realistic way. And then the algorithm becomes a bit longer. We have another for loop where we go through each decision stage K. And now the algorithm also requires an adaptive decision policy theta that determines how the decisions are adjusted based on the realizations of uncertainty. We can expand this algorithm. We can make our analysis more realistic in this way, but we also make it a bit more complicated. We have to define an adaptive decision policy. And if we define many decision stages, then the computational effort will probably increase. So that's the downside. I'm going to skip this for now because I don't think we have time. So in summary, we have these 3 versions of analysis that one could do. And we're arguing in this paper that people should be doing more of this robustness analysis, and especially the adaptive version, if we're actually considering long time horizons. So we can apply this to our solution, to our case study, where we do 1,000 scenarios that we generated, and we do these 3 versions of analysis. In the first, we can adapt all of our decisions. In the second, they're all fixed up until 2050. And in the third version, we fix decisions for the first 5 years up until 2030, and then we can re-optimize every 5 years. Well, we see very different results for the 3 versions. Here in sensitivity analysis, we see that the objective value could be almost 40 billion under the right scenarios, but it could also be as low as 10 billion if we're unlucky. And the dotted line indicates the nominal objective value. The static robustness analysis is a lot more pessimistic, of course, because here all our decisions are fixed. We don't get to re-optimize anything. And here we see that some of these scenarios can actually reach below 10 billion euros. So here we're getting in danger of not turning a profit. And the 40 million seems far out of reach if you use the analysis on the right. The adaptive analysis provides you something in between, where the picture is more nuanced and more realistic, we would argue. You can also plot the same graphs or the same data as cumulative distribution functions, and you see that the adaptive analysis is nicely in between the other two. Okay, one thing here to mention is that robustness analysis is not only more realistic or more interesting in our opinion than sensitivity analysis, but it can also be done in less computation time. Of course, because in the static analysis, we're not re-optimizing anything. So it takes milliseconds to evaluate how well a solution performs for other scenarios. In this case, we're not doing any solving. In the adaptive analysis, we do some resolving of the later stage decisions, so it does take some solve time. But in this case, the sensitivity analysis is taking the most computation time per scenario. And we also evaluated our analysis for a different number of decision stages. So we were here where we had 5 decision stages in the initial analysis, but you could also do 21 decision stages if you were to re-optimize every year, and then it would take you 50 seconds for solve time. Okay, we're not saying that sensitivity analysis is useless, because it is actually quite interesting, the information you get, because you can use this information to calculate the regret. If you take the sensitivity analysis results and you subtract what you got with robustness analysis, then you can find out what is my regret here per scenario. Under a given scenario, how much could I have done if I had made optimal decisions for that scenario, and how well am I actually performing given the decisions that I had to fix. So here you can see that for some scenarios, we really wish that we could make different decisions because our regret is almost 10 billion, or more than 10 billion. In this case, this picture of regret can change quite can change quite a lot based on which version of the robustness analysis we used. So on the right, we see the adaptive methodology, which is more realistic. And it shows us that the methodology you use really matters. If you use the picture on the right to make your decisions, you might make very different decisions than using the picture on the left. Okay. So far I only showed the objective function, the total objective function, but you can also look at other outputs, of course, using the analysis. I won't dwell on it too much here because it's not so interesting for this audience. But the question remains, could we get a more robust solution? Maybe you show this to your stakeholders and they say, oh, I'm not really happy with this graph, a regret of 5 billion, doesn't taste, I don't like the taste of this. Can we get a better solution? Can we do better than this? So that brings us to the domain of robust optimization, which all of you know very well, I'm sure. And we go back to this sad finding from the review study by Yu et al., where the least popular methodology was robust optimization. And we saw this and we were a bit discouraged, and we wanted to see, can we improve this? Can we propose a new method that is more friendly for practitioners, something that is maybe easier for people to utilize in practice? So we came up with a new algorithm that we call ROBIST, which stands for Robust Optimization by Iterative Scenario Sampling and Statistical Testing. And the nice thing about this algorithm is that it's really only, you could think of it as applying robustness analysis, but in an iterative way, where we keep analyzing solutions iteratively. It's quite a simple algorithm, in our opinion, and you can apply it to a wide variety of problems. So we're hoping, because it has these characteristics, that it's going to be maybe a more popular method for people to use in practice. And in the paper, we also did a number of numerical experiments where we can show that this algorithm performs quite well. I'm not going to go over these experiments in this presentation today, but if you're interested, you can read the research paper. To give you a bit of an idea, a sketch of how the algorithm works, we take a bit of a machine learning approach where we have a data set containing a number of scenarios, and then we split the data into three subsets: a training set, a validation set, and a test set. We ask the user to specify a risk tolerance and a statistical confidence level, although the latter is optional. And we require a stopping criteria, either a certain time limit or an iteration limit that they want to impose. And then what we essentially do is we iteratively optimize for a small set of scenarios. And we do this to generate new solutions, xi, where it's very important that our set of scenarios, si, is kept as small as possible. Then we analyze the robustness of our generated solution using the validation data set. If we're happy with the robustness, we can stop. If we're not happy, we add more scenarios to our set of scenarios, Si. I should mention, so if we find that our solution is too robust, we can also remove scenarios from the set Si. So that's in a nutshell what we do. And then at the end, we give back the best found solution, and we can also give a statistical guarantee using the test set about how robust this solution actually is. Okay, so we applied this algorithm to our case study problem, and we got a new solution, the one we see on the right, where we really focus on these first stage decisions, investment decisions. And we find that the robust solution invests less in hydrogen in the first year and more in infrastructure, and also a bit in CCS in 2030. And then the nice thing is we can use robustness analysis to compare these two solutions and evaluate, is my robust solution actually more robust than my initial solution, the nominal solution? So we do this in this slide. We find that, of course, for the nominal scenario, which was the dashed line here, our performance decreases because the nominal solution was optimal for the nominal scenario, and the robust solution is not optimal for the nominal scenario. But the other scenarios, we have a different performance, of course. And it's not very clear in this graph, but here we see that the robust solution does have quite a different performance for these alternative scenarios, and especially visible in the regret histogram. Because here we see that the regret distribution is really a lot different. The purple distribution is quite different from the green distribution, where we're able to cut off a lot of the tail in terms of regrets. And here we don't want to attach too much to the probabilities and the likelihood of things, but based on our test set of scenarios, we are able to reduce the empirical regret by 413 million, which is quite a nice number. And our estimated probability of having a regret larger than 2 billion is reduced by almost 20%. Okay, so that was it. Now for the conclusions. Robustness analysis, it's a term that is not very popular, but we would like it to be more popular because it's quite an easy thing to apply. It gives you a lot of interesting information, and it should be used as like a first step, as a screening procedure, pre-robust optimization. We show that we can extend it to a more realistic adaptive optimization setting, and we can do this in a computationally tractable way. And we show that we can use robust optimization for these real-world case studies in a very effective way. And in this case, our algorithm that we proposed worked quite well. And we show that it works quite well for a variety of problems. So that was it from my side. If you're interested in the details, you can read the research papers. They're available online. And yeah, thank you for listening. Let me know if you have any questions.